Hello, guys. Thank you very much for coming to the class. I'm saying hello, but I think the only one that can hear me is Quiroz Montoya. Can everyone hear me? Good one. 3 people in the camera. Please turn on your cameras to see you. Thank you very much. Eva, Rivaldo, Bernardo. Rivaldo was a good soccer player, by the way. So thank you for coming to the class. And today we're gonna actually start a new method. But before I want to make sure that you understood all the exercises that you were going to, or you are supposed to do actually. So do you have any question about the exercises? No question at all? So far, everything is fine. So we're getting less people every time I come. So, so I'm actually kind of like surprised because you're now 7 people. But that's fine. I mean, as long as we're 7, we can teach the class. So today we're gonna then, if you don't have any more questions, today we're going to discuss a new method. So we are still, again, we're still in the solution of algebraic and transcendental equations. So we are still in the same unit. So on this unit, let me tell you, is actually one of the longest units because it requires a lot of review and also a lot of methods to solve this type of equations, because in general in engineering, those are one of the most useful methods. We are going to start later. We just have, I think we have 3 methods left, and then we move to system of equations. So we're moving in a good pace. Just let me know if I'm actually going too fast. I'm trying to speak very slow today because the other class said that I was speaking too fast. So I need to speak slowly so that they will be able to understand what I'm saying. So don't get scared about me speaking too slow. So this new method, the method we are going to discuss today is actually what we call the Newton-Raphson method. Okay, it's actually referred to in literature a lot as the Newton's method. But in general, it's Newton-Raphson because these 2 guys, Newton and Raphson, actually got together and developed a well-suitable method to solve transcendental and algebraic equations. And actually, the Newton's method can be used also to solve linear system of equations and nonlinear system of equations. We are going to see later that we are going to use the nonlinear Newton's method in this class, because when you take you take it, probably you have a class of hydraulic machinery or hydraulic systems, right? I'm assuming that you have a class, an experience or course on those topics. I don't know, ¿ustedes son mecánicos o civiles?
Civiles, profe.
Okay, civiles. So if you're civil, you will actually take the class of hidráulica de tuberías y canales. So in that class, if you are actually planning on taking it, so you will see that you need the Newton-Raphson in the nonlinear version to solve the system of equation of a network of pipes. They actually call it pipeline networks. So that's why this base of the Newton-Raphson method is very useful when we move to the nonlinear version used for a system of equations. You can do this actually very, very accurate, and we will be using several tools as like Excel or MATLAB. Okay, so one of the characteristics of the Newton method is that it usually converges much faster than the linearly convergent methods. So it means like the Newton method converges faster than what? Converges faster than the Of course, the graphical method, because we already know this is not numerical though. But we have also the fixed point iteration. We have the bisection method, right? So this method is actually faster. So this is one of the advantages of using the Newton's method. So essentially, what we're doing in the Newton's method, it's, you know that if you have a line here, of course, a line, and then you have a certain curve. So this line is actually giving you the secant of this, not the secant, sorry, the tangent of this line. That's the concept of the derivative, right? If you remember, this is a tangent here as to the function f. Let's call this a function f. And then, of course, the secant, sorry, the tangent is this one, and it touches, or it just intersects the line at x0. So this is the solution, the first initial guess for the Newton's method. Okay, so essentially when we make the first iteration, we're touching the curve. And then when we make the second iteration, we're going to touch another point until we actually reach the solution of the curve. We already know that the solution, for example, of this curve, or this function, is actually going to be close to -1, for example, right? So what we're doing, just moving the tangent to this line until we obtain the solution or the intersection with the x-axis. Okay, so that's why the tangent will be approximately follow the function down to the axis toward the root. So it's just going to be moving. So if I'm using, well, I don't have the, no, this is not made in, this is a PDF. But in general, I'm going to move to this point, and then to this point, and then to this one, and then I'm going to get very close to this point so that the intersection point of the line with the x-axis, it's an approximate root. Probably won't be actually the exact solution, but it's going to be a very good approximation. Okay? So, and then if we just need more precision, we continue iterating. Okay? But in general, that's how the Newton-Raphson method works. So that's why if you see that we're using the derivative of the function, we have to use the derivative in this class. So it's very, very important to use the derivative. Okay? So in general, if you think about how to obtain the Newton's formula or the Newton's method formula, we go to what we develop at the line, at the formula for the line function. Do you remember la función de la línea entre dos puntos? That's why they call it. So remember that it was actually y menos y1 igual a x2 menos x1 sobre y2 menos y1 por x menos x1. ¿Se acuerdan? Algo así. So that was actually, that's the function for between 2 points. So that in general, if you think about it, we're actually using 2 points. We're having 1 point here to create a line, but this line is just related to the tangent of the function. So this is the point slope formula for the equation of a line. That's how we call it in English. So the point slope formula. Okay, so if you see, this is actually y minus y0. If you think, or y1, what do you call it? Y menos y1 igual a la pendiente. So remember that the slope of a function is actually the derivative of the function, right? So if we think about the slope, we're thinking about the derivative. Let's just go to Google to remember a little bit of this. So I'm just gonna remind you, because it's very important for you to actually connect all the knowledge that you previously got. So let's just get it in Spanish. So ecuación de la línea recta. So this is actually the equation that I'm going to talk about. I'm pretty sure that this is probably the one. And this is the tangent. Remember the slope of a function? So this is like this one. So it says, oh, correcto, yeah, right. So I got it because this is the, the tangent. Recuerda que la pendiente es la tangente del ángulo de inclinación de la recta respecto al eje X. So this is the correct one. So this is, you already know that is y1 minus y2 divided by h1 minus x2. So this is the line. But in general, if I go here you go, you have this equation. So y minus y0 equal to the slope of the function that is defined by this formula. And in general, it's actually the derivative of the function times x minus x0. And if you compare what I have here, it's exactly the same. So I have y minus x, the function f evaluated in x0 equal to the slope of the function times x minus x0. So this is exactly the same function that you previously saw in many classes. This is the one you saw in other classes. In Geometría Analítica, that's the when you use it, I think. So continue this. If you think about this, we just actually can make some arrangement of this function. So remember that we are looking for the intersection point of the tangent line with the x-axis, right? So, and in general, for this we have to assume that y is equal to 0, because in this case y is equal to 0, right? This is the tangent. The condition to be here it's that y is equal to 0 and x has certain value. So here we are assuming that that y is equal to 0. So if we have this equal to 0, we have just making a mirror of the function. So we have the derivative times x minus x0 equal to 0 because y is 0 minus f x0. So we just want to actually, rearrange it. We multiply this one times this one, and if you get it. So we just actually multiply it, or actually this is 0. Oh, sorry, not multiply it. Actually, you pass this to dividing this function. So you divide this function here, and then you have the initial value. We just pass it to the right-hand side of the equation. So you have this function as the Newton's formula. And if you think about it, now that you know more methods, right? So if you think about it, this line, what is this? What is this in general? ¿Qué forma tiene de acuerdo a los métodos que hemos visto en clase? Hemos visto dos numerical methods. ¿Qué forma tiene? ¿Tiene acaso la forma de fx igual a 0 o de gx igual a una función? ¿Qué fórmula tiene? ¿Qué forma tiene, perdón? Hemos visto dos métodos. Bueno, tres, pero hemos visto dos numéricos.
Creo que
es una ecuación diferencial de primer grado, ¿no?
Well, yes, but in general, if you think about this formula, it's actually gx equal to something. So if you remember in the previous classes, we were discussing fx igual a 0, era para el método de bisección. Y gx igual a una función, como por ejemplo hablábamos de gx igual a coseno de x, tenía una forma que gx estaba en el lado izquierdo y coseno de x en el lado derecho. Mientras que si nos íbamos a la función de la bisección, era fx igual a 0, siempre. So if we think about this, this actually has a fixed point iteration form, because this is x here, and this is x0 minus certain value. Así es como ustedes tienen que expresar su función, ¿se acuerdan en su tarea? Algo muy similar. Tienen que dejar x de un solo lado y esto va a ser igual a cierta cantidad o cierta función a la derecha, right? So in general, this is actually sort of a fixed point iteration formula. So if we actually solve for x gives for x, we are actually going to have the first approximation for a root. So we just provide an an initial guess, x0, and then we solve for the first approximation. This first approximation, we are going to call it x1, and next, the entire process is going to be repeated, and then we use x1 to produce x2, and so on and so on, okay? So this is in general, again, an iterative method. We are just iterating and iterating and iterating, okay? So, for example here, so we have that the Newton's method is actually an initial guess, x0, and then the xi plus 1 is going to be what? It's going to be xi minus the function divided by the derivative evaluated in what? In f0. Because this is the first guess. So for I equal to 0, 1, 2, 3. So here is 0, and then in this case is going to be x1. It's pretty similar to a fixed point method, but if you think about it, we are just including what? The derivative of the function. So that's why this is very, very efficient. Okay, so in general, we can actually have an example. So in general, we have this. So we have this formula, or this equation, sorry. It's x to the power 3 plus x minus 1, and this is equal to 0, right? So if we calculate the derivative of this function, we know that it's going to be 3x squared plus 1. This is the derivative. So correct. So what we need to do is to put these two functions as in the form of the Newton's formula. Okay. So in general, xi, which is this one, is going to be equal to xi minus the function, which is this one. But now we introduce in this function the subscript I, which is this one, xi to the power 3 plus xi minus 1. And this is going to be divided by the derivative. So the derivative in this case is equal to 3xi to the square plus 1. If we actually make some arrangement or some algebra in this formula, so we just multiply this one times this one and 1 times this one, so you'll see that we obtain actually this formula at the end. Okay, so we just multiply this one is going to be 3x squared, 3x cubic actually, and this plus xi. So xi's, the two of this, they're going to be canceled because one is negative and the other one is going to be positive. And then this is going to be positive and this is going to be negative. So 3x squared minus xi to the power 3. So 3x actually, 3xi to the power 3 minus xi to the power 3 is going to be, one of these is going to be subtracting. And I'm going to have 2xi to the power 3 plus 1, because this sign is going to be multiplying this minus 1. It's going to be plus 1, and then we're going to have the same denominator in this formula. So it's pretty easy to actually obtain this type of formula. Okay, so we obtain now the Newton's formula for this equation. This is the Newton's formula for this equation. Okay, so in general, we moved actually to the next slide, and then we, using this equation, we just compute for the initial value, for example. So x0, let's just suppose this is a guess, remember. We're guessing, so it's equal to minus 0.7, and we obtain that if we substitute 0.07 minus 0.07 in this equation, we obtain the x1, sorry, equal to approximately 0.1271. And then we use the 0.1271 and we obtain in the same form, we using the same formula, we obtain approximately equal to approximately to 0.9577. So to illustrate the equation, we started with minus 0.7. This is the initial value, right? Then we have the derivative. This is the tangent. For the second one, it was actually 0.12. So we're in 0.12 here. We obtain the secant when x is equal to 0.12. It's here. And then we obtain the next one. And then we obtain here is actually 0.95, right? And we already know that for the curve, which is this one, the solution is going to be about, I don't know, like 0.7 something, right? So we are just, moving the tangent throughout the line until we reach this point. Okay, let's actually do this example. You want to do it? Well, let's do it in Excel. So I think it's better if we do it in Excel. So I think this is the one, right? Yeah. Yeah, I think this is the one. So yes, this is the one. Okay, so pay attention of the Excel value. Sorry, of the Excel sheet. Remember that the initial value was minus 0.7, right? So in general, I'm going to actually just, for the sake of my exercise, I'm gonna paste it here, so, just for the sake of this. So we are gonna just delete this one, and then we are gonna do this again. You can follow me if you want. So it's gonna be useful if you follow me. So first of all, I only need these two for the moment. Focus on this line, on these two columns. So this is the number of iterations. And then I just write my 0.7, which is actually my initial value. Okay, so I have my initial value. And then what I need to do is to use this formula for the next value. So if I use the formula is going to be 2, well, actually parentheses, 2 times this one, right, to the power 3 plus 1, parentheses, dividing, open parentheses, 3 times, whoops, well, this value, this one, yeah, to the power is 2 plus 1. So this is the formula, right? So this one is 2 times the previous value to the power 3 plus 1, and then divided by 3 times the previous value squared plus 1. Ta-da! There you go. You have 0.1271255. So this is what you get in the first iteration. You see this? It's pretty simple. That's why I love numerical analysis. Numerical analysis is simple. Well, not that simple because sometimes I have problems that I cannot even solve. But in general, what we see in this level of education is actually pretty straightforward. So how do I calculate the other two one? This is easy. Look, this is magic. This is what I love of Excel as well. So you just, boop, and that's it. Again, you see this square corner here. You put it here, and then ta-da! That's what you get. So that's how you get your solution. If you see in the plot here, it's about 0.7. Yes, it's about 0.7 because the solution is actually 0.68, 23, 27, 80. So that's the solution. So what do I do here? So this is something that I'm going to discuss later. But in general, if I see that this is the value that has a good convergency, so I would assume that this is the real solution. So what I do is just to calculate the error. So in general, to calculate the error, you already know how to calculate the error, right? The error is actually equal to the absolute value of this one minus this one, right? But I'm going to block actually this one because this is my true value. So my true value with F4, I block it, and that's it. So I got my error. This is my true value. So if I actually do the same for this column, soon. So you see that this one minus the same one is going to be the error is going to be equal to 0. Actually, from the sixth iteration, the error is equal to 0. So we only needed 6 iterations to reach a good approximation. Of course, this is something that I'm going to explain later, but in general, what I'm doing is just actually using the error, the current error divided by the current, sorry, the previous error. So same thing. So what I just do is just, do this and you get the same. But this is just an operation that we are going to use later. Don't worry too much. The main thing that I need to understand is this one. And probably the error, because the error is decreasing. So you'll see that the error is actually decreased very, very fast. Decreases very, very fast. So did you get any question about this? Any questions about this process?
Yo podría volver a repetir lo que está en la columna C de Excel. Es que lo veo muy chiquitito. Es I igual al valor absoluto de X1 menos R. Ajá, no entendí muy bien.
So remember, this is the value of the xi at the iteration 0 minus the true value. The true value. I'm assuming that the true value is when the error is equal to 0, or when the true value doesn't change a lot. You see that in these two iterations, the values are the same. So it means like I'm reaching the true value. That's why I'm actually just blocking this cell. Para bloquear una celda, lo único que tienen que hacer es ponerse arriba y le ponen F4. Y se bloquea. Entonces bloqueo la celda para que este siempre sea mi valor verdadero y le quito yo a todas mis aproximaciones, le quito el valor verdadero. Y así obtengo el error. Si vieron el error en la sexta iteración, ya es 0. Quiere decir que alcancé what I call the true value. Although it's not the true value, but we are assuming that this is the true value. Okay?
Okay, perfect.
No problem. That's what is the class for. So any more questions? No? Pretty easy? Fácil? Right, okay. So let's continue with this now. So this is what you already saw. If you remember, this is what we got here. I'm just, putting this back here. So this is what we got. So what can we observe here? So we need only, first of all, we need only 6 steps, and the root is known to the 8 correct digits. So we need up from the 6th iteration, the error is actually it's 0.1 to the power minus 8. So that's a very good approximation. It's a very, very low error. But there is something a little bit more that we can say about, the error. So for example, here, you see actually that the error it's 1.38, and then it's 0.55, and then it decreases to 0.25. So it's actually, let's just consider this. This is actually reducing a little bit like by half, right? The error is almost by half. And then we have this one is almost by half. And then suddenly, boom, the error is actually less more. Here is a lot more less than the previous one, and here is just way more than that, right? So we're seeing that once the convergence starts, the number of correct places in xi, this is xi of course, the number of correct places is actually doubles on each iteration. Yes, right? Because you have here, the iteration starts here. So this is just the beginning, takes place. But after the fourth iteration, you'll see that you have here 2. And then for the second one, you have 3. And then for the other one, have 8. So actually, it doubles the number of correct digits, doubles on each iteration. El número de dígitos correctos prácticamente se duplica en cada iteración. Okay? So that's one characteristic of the Newton method. And this characteristic is called quadratically convergent method. So the Newton method is a quadratically convergent method. If you remember, the bisection method and the fixed point iteration method were what? Were a linear convergent methods, right? In this case, this Newton method is a quadratically convergent method. So uno es lineal, este es cuadrático. That's why it's actually, it doubles each iteration. So that's a good definition. So, but then we have to study a little bit of this thing, right? Because we need to understand what was going on. Okay, the convergence, as I told you in the previous examples, it's faster than the linear convergence that we saw when we use the bisection method and the fixed point iteration. So it's faster. Now we prove that by doing one exercise. So if we actually want to prove this, we have to do it just by saying that the error, in this case, after the step I or the iteration I, the iteration is actually quadratically converged if m is equal to the limit of the error or the future error divided by the current error to the power 2. And this, of course, has to be less than infinite. So here, this m value is actually equivalent to what we call S. If you remember, S was actually the slope of the function when we had linearly convergent methods. So in this case, so it's not S, we name it M. So it's a different letter, and it's a different condition. One is linear, one is quadratically convergent. Okay, so if we actually consider any function f, let f be twice continuously differentiable and fr equal to 0, right? So remember that fr equal to 0, it means like r is the root of the function, right? This is the root of the function in the previous exercises. So if the derivative of fr is different than 0, then Newton's method is locally and quadratically convergent to R. So see carefully here, because this is pretty much the same thing that we were discussing in the previous exercises, especially in the fixed iteration method. So if the derivative of the root is different than 0, then Newton's method is locally and quadratically convergent to R. So this is very important. Aquí estamos hablando que si la derivada evaluada en R es diferente de 0, el método de Newton es locally y cuadráticamente convergente a R. Okay? And of course, if this is actually satisfied, the error EI at the step I satisfy the previous condition. This is the previous condition equal to M, where M in this case is going to be equal to the second derivative. That's why we need to actually that the function is twice continuously differentiable divided by 2 times the first derivative of the function. So this is how we compute the M value. Así es como calculamos M. En el otro calculamos S, ¿se acuerdan? Cuando sacamos la primera derivada y poníamos la raíz, sacábamos una pendiente. En este caso hacemos algo muy similar. M la obtenemos de la segunda derivada evaluada en la raíz, dividido sobre F, sobre la primera derivada evaluada en R. Vuelvo a preguntar, profe, pero ¿cómo podemos sacar R si estamos apenas resolviendo el problema? Es algo que parecía tonto, ¿no? Oiga, profe, me está diciendo que esta es una cosa que tengo que obtener para saber si tiene solución, pues yo no tengo la raíz. Claro que sí tiene la raíz aproximada, pero la tiene. Ya sabemos que el método gráfico es un método que nos puede ayudar a calcular al menos la raíz aproximada. M te va a dar una raíz aproximada, una R va a ser una raíz aproximada visualmente y ustedes pueden calcular M más o menos con cierta precisión. Okay, so that's why we need to actually incorporate all the knowledge that we have been doing these days. Okay, so let's just continue explaining the mathematics of this. I know this is actually very tedious. It's just boring because you don't like mathematics in general. You like more like to be practical, but we need to actually study this. So in general, to prove this local convergency, we need to analyze the function of the Newton method. So the Newton's method formula, as I told you, at the very beginning of the class, this class, is actually a fixed iteration point form. So in this class, if we go back to the Newton's formula, this is the Newton formula. This could be called gx is equal to x minus fx divided by the first derivative of x. So it's actually a fixed iteration formula. If we actually consider a fixed iteration formula, we can compute the derivative of this formula. So the derivative of this formula, ¿cuánto sería la derivada de esta fórmula? Para que no se me aburran, porque los veo como muy cansados, como de tanto que hablo. ¿Cómo sería la derivada de esta fórmula? A ver, ¿quién me lo dice? Por supuesto está abajo, pero quiero algo más productivo, ¿no? ¿Es correcto acaso esa derivada? Por supuesto, la derivada de x, ¿cuánto es?
1.
No.
Y ahora la segunda derivada es una ¿qué? ¿Qué forma tiene? La otra parte, el segundo término. ¿Cómo la derivamos? ¿Es una qué?
Es U sobre B, ¿no?
Exactamente, U sobre B, ¿no? Entonces acuérdense que U sobre B, ¿cómo va? ¿Cómo era la fórmula? Es
U por la derivada de B menos B por la derivada de U sobre
Exacto.
B al cuadrado. Entonces,
exactamente. Entonces ya tienen aquí, por supuesto, que esta es B al cuadrado. Aquí está. Lo único que necesitamos es probar esto, ¿no? ¿Cierto? Y si decimos que es U por la derivada, ¿cuánto es B por la derivada de U? Sería prácticamente es esta por la derivada de esta, ¿no? Entonces sería derivada al cuadrado menos esta, la U por la derivada de B, que sería la doble derivada. Si analizamos, dividimos esta entre esta, me queda 1. Este 1 con este 1 se va y solamente me quedaría fx es igual a la doble derivada de x dividido entre la primera derivada de fx al cuadrado. ¿Cierto? And now if we actually observe this, if we have the root, any root of this equation, so we will observe that the GR sorry, the first derivative of the g function evaluated in R is going to be equal to 0. Okay, so Newton's method is locally convergent since it converges to R for initial guesses sufficiently close to R. So this is the proof actually that we are seeing a local convergence here. So it's pretty much what we're doing here, right? So now we prove that it's locally convergent, right? But we need to prove also that it's quadratically convergent. How do we prove it? So we have to use actually another perspective. We're going to actually use more tools because in this case it's not that easy. So we're going to just keep track of the error term in each of the steps of the Newton's method. Okay? By error, of course, we mean the difference between the correct root and the current best guess. Okay? So that's what we mean by error. Okay? But for this type of the derivation, we're going to use what we call in calculus the Taylor's formula. Remember, Taylor's formula tells us the difference between the values of a function at a given point and another nearby point. Okay, so this is what we use in calculus when we use it, the Taylor's equation, Taylor's formula, la fórmula de Taylor, ¿cierto? So in general, I'm just going to actually put this. You remember, I took this one from a calculus book. So this is the Taylor's theorem. And I'm assuming that you saw this before because you took calculus. Ya vieron cálculos, ya tuvieron que haber visto el teorema de Taylor, o al menos la función de Taylor. So this is actually what we have. This is the entire Taylor's formula. So it has a bunch of terms. It's a very long formula, right? And it can has n degrees. You know, like you can actually extend it to infinite if you want. However, this is not the case for us. So what I'm going to do is actually to cut off these formulas until the quadratic term, because we are trying to prove that this method is actually a quadratic method, a quadratically convergent method. So that's why I'm going to cut out these terms. I'm just going to take this one and then use it as this one. In this case, f r, which is the function of the root, is going to be equal to what? To the fxi plus r minus xi plus the first derivative here of xi. So you see here that c is actually the value of xi times the derivative is here, plus, in general, if you remember, we were discussing that this term here is actually what? If you come back to this part, we define it by the error, in this case, to the square, divided by 2 times the second derivative. Okay, so we just miss actually the factorial. If you see here, I miss the factorial, so just be aware of this. So I miss it here. But in general, this is the Taylor's formula. Okay. We are analyzing the difference between 2 different points. That's what I said here. That's why we're using this term. Assuming that the other terms are actually negligible. Despreciamos los términos cúbicos, cuartos, todos, ¿no? Okay, so let's analyze this equation. So to be able to solve this equation, to be able to solve it, fr has to be equal to what? To 0, right? Because we said like if r has to be equal to 0 to be solved. So that's why we have 0. And in general, we are going to use all the terms in the Taylor's formula. So this is fxi plus r minus xi, which is this one, plus fxi plus the same thing, which is actually the error here, 2 squared divided by 2 times f to the second derivative of ci. So what I want to do now is actually simplify it. So what I do is divide all this equation by the first derivative of x. I'm defining the first derivative of x. Okay, so I divided this by the first derivative. Yes, it's like this, and I actually send it to the left-hand side of the equation. It's here. And then if I divide this term by the first derivative, it got canceled out, and I got only r minus xi. Plus, of course, it's going to be the same term, the second derivative, and then divided by the first derivative. Lo que hice fue dividir toda esta ecuación por la primera derivada de fxi. ¿Ok? Entonces lo tengo ahí. Listo. So we are assuming, of course, because that was the assumption that the first derivative was not equal to 0. This is one of the assumptions we were here. Divided that this is different than 0. So we are assuming that this is different than 0. So we can rearrange this as if we actually take these two, we take it to this side, so it's going to be positive x minus this term, and this is going to be a negative r. Right? And this is going to be equal to, of course, this term completely. So what do we know here? So what is this? ¿Qué es esto? ¿Qué tienen ustedes aquí? ¿Qué es esto que estoy subrayando? ¿Qué es? Lo hemos visto en la clase. Hicimos un ejercicio.
El método de Newton.
Exactly. So, because it's the Newton's method formula, so this is equal to xi plus 1. So in general, if we actually use it, this is it. So this is going to be xi plus 1. So I got xi plus 1 here, minus r here, and this is equal to, we are using the concept of the error. La raíz menos el valor como tal actual de xi va a ser igual al error, a la distancia que hay, si se dan cuenta. Si yo tengo una raíz menos el valor actual, siempre va a ser el error. So this is actually the error to the square, to the power 2, sorry, or the square error. And then we have this one. So, but in general, this one is also an error, but this is the error for the what? For the iteration I plus 1. Because this is xi plus 1 minus r. So the last formula, the entire formula is then ei plus 1 is equal to ei to the power 2, and then times this term. And what is this term? So if we go back again, what is this term? M, right? It's M. So now we actually got, by just simply observing the error in the formula, we obtained the M value. So M at the end is ei plus 1 divided by ei squared. So if we go back again, this is M, right? There you go. So the same thing. So it's actually, it's probably difficult for you to understand it, but in general, it's just a follow up of the Taylor's formula. So it's just very simple, and it's a very nice approximation. This is only a proof. So I'm not trying to actually, you do this in your exercise, you don't have to prove anything, because this is not the case, at least for numerical analysis. But I'm just giving you the proof that the Newton's method is what? Is linearly convergent, sorry, is quadratically convergent, and also is locally convergent. This is the way we prove that this is actually quadratically convergent, and this one was the proof that is locally convergent. Okay, so that's what we have now. So again, you see that this is the definition of the error. In general, that's why we obtain this. And then finally, we obtain, if we move this to here and send it to the limit, we obtain that this is going to be equal to M. Or in general, the error or the current error, the future error in the step I plus 1 is approximately equal to m times the error square of the current approximation. So this is just a simple math, right? We just send this one to this one, and then we got this one. So remember that this is m in general. Okay, so remember m. If I ask you somehow to calculate the value of m, this is how you have to obtain it. Si te pido cómo calcular el valor de s, ya lo sabemos porque es lo que ustedes van a hacer en su tarea del Fixed Iteration Method. Porque ustedes van a calcular el valor cada vez que tengan que modificar para poder solucionarlo, para poder solucionarlo, van a necesitar ustedes sacar la derivada para saber si es menor que 1. Okay, so remember that. So in this case, m is equivalent to this. In the FPI method, el valor de ¿qué? De la derivada evaluada en R, y tiene que ser menor a 1, y para el método de bisección S es igual a ¿qué cosa? A un medio, porque estamos haciendo una bisección, dividimos entre dos símbolos. So which one is faster? Of course, the Newton's method. Which one is faster? Then the second fastest method is going to be the FPI, and then the slowest method is going to be the bisection method. So this is the rank of how fast you solve a problem using these three methods. ¿Alguna pregunta hasta aquí? Pretty easy, right? Great. Cool, thank you. So if we move back, so we obtain this in general. So we can actually use the Newton's method to solve this equation, for example. So how do we use it? This is actually a very good way to actually show you something. So remember that the method is actually quadratically convergent. However, I didn't say that it's always quadratically convergent, right? I said it's quadratically convergent, but I never said that it's always quadratically convergent. So this is tricky, right? Because remember that the method is actually divided by the derivative of the function, right? However, this is not the case for certain cases. So if we actually use the Newton's method for this function, fx equal to x squared, so ¿cuál es la derivada de x squared? What is the derivative of x squared?
2x.
Exactly. So we just actually put it as a function. So xi plus 1 equal to xi, which is the Newton's formula, minus xi squared, which is this one, divided by 2xi. All right. So we can actually cancel out this operation, these terms, right? So we cancel out 1 degree of the numerator, and then we're going to have that in general, xi plus 1 is going to be equal to xi divided by 2. Why? Because I have xi minus xi divided by 2 is going to be a positive xi divided by 2. If we analyze then, the derivative of this function is going to be 1/2. Si analizamos la derivada de esto, es un medio. Por lo tanto, si es un medio, entonces se nos igualó a ¿qué cosa? Al método de la bisección. And if we try to solve this in Excel, for example, I don't know if I actually have it here. No. Oh yeah, it's here. So I think it's the same. Yeah, just check this out. So we're just gonna do it. So I just have the initial value equal to 1, and then my next value is going to be equal to, of course, this formula, xi divided by 2, which is 0.5, and then Ta-da! So it took actually 16 iterations to obtain a decent value of the error. 16 iterations. And then, guys, ahora ustedes se acuerdan que había dicho, oye, pero profe, ¿por qué utiliza esta vaina, no? ¿Por qué pone esta última columna? Ahora ya tiene sentido, ¿no? Vean cuál es el valor de m en este caso. Un medio. ¿Por qué? Porque acuérdense que el valor in this case is actually defined by this one. M is this. If you analyze actually the second derivative of this one, it's going to be 0 because you only have x and then you have this one equal to this one. Then you will have only 1/2. That is why we have 1/2 here. So in general, the m value is going to be also obtained by the error divided by the previous error. So in this case, if you think about it, so this is the value. So this was about 0.85, the m value. Sorry, I made a mistake here. This one, so it's just pretty much the same, but it's going to be equivalent because you only have 1/2. So this is why we obtain this value. And then we see that not always we have rapid, a fast convergence. It took 16 iterations, so that was actually very slow. Okay, let's move forward to other examples. So if we actually want to generalize this case, instead of having x squared, I have xm for any value of m. So we have this form, right? xm for any positive integer m. Okay, so the Newton's actually equation is going to be equal to this: m fx is equal to x to the power m. Any of those. Okay, so in general, if we want to actually make sense of the formula that we saw previously, so the Newton's formula is going to be xi plus 1 equal to xi minus the formula, the equation, xim divided by what? To the derivative of this. What's the derivative? m xi n minus 1. This is the derivative, right? And then xi plus 1, if actually you simplify this one and multiply this one times this one and then make all the arrangements, I'm going to have that xi plus 1 is going to be n minus 1 divided by m xi. Okay, so here the only root is actually r equal to 0. So we define the error as xi minus 1. So, and then this is going to be equal to xi. And then the error of the future step is going to be equal to s times the current step. And we already know that the m value, because here we saw that it was 1/2. In this case, we're going to have the error is going to be m minus 1 divided by m. O sea que si tenemos x cuarta, por ejemplo, en lugar de x cuadrada, va a ser ¿qué? 4 menos 1 dividido entre 4. 4 menos 1 es igual a 3. Entre 4 sería 3/4. Va a ser en este caso el valor de s o el valor de m para esta función. Si tuviéramos un valor de 5, va a ser 5 menos 1, 4/5, y así sucesivamente para este tipo de funciones. So we are just generalizing the functions. Okay, that's what I mean when I say that's one. Okay, so let's continue. So let's actually let's apply the Newton method, and we're going to find something very nice. So in this case, the example number 1 says, find the multiplicity of the root r equal to 0 of x equal to sinus of x and x squared times cosinus of x minus x squared minus x. Okay, and estimate the number of steps of the Newton's method required to converge within 6 correct places. And it says, use please x0 equal to 1. So remember that this has to be always is gonna have when we're using trigonometric functions, we want to use always the calculator in radians. Okay, so that's very important. Okay, so this is the function. So how I compute the multiplicity? So the multiplicity, I compute the derivative until the function is actually equal to 0. So, while evaluating in 0, of course. So then the derivative of this function is sinus of x equal to cosinus of x. This function is a u por una u por b, derivada de u por b menos b por derivada de u, negativo. Digo más, menos, se vuelve negativo, ¿no? Right? Minus 2x minus 1. So easy, piece of cake. So next, the second derivative. So cosine of x, this cosinus of x is minus sinus of x. This is this derivative. It's again actually a what? This is an uv function. So again, derivative of this one times this one minus derivative of so derivative of this one, which is minus sinus, times this one, derivative of this one. I think I made a mistake here, right? Esta derivada sería 2x, sería 2 por coseno de este, menos, en este caso sería 2x, ¿cierto? Menos seno de x. Aquí hay un error, ¿cierto? Este es 2, debe ser 2, right?
Sí, profe.
Yeah, so there's a mistake here, so this has to be equal to 2. And then we have that x squared times cosinus of x. So this is the same thing, right? Oh, wait a minute. So no, this is actually a u divided by b. So u times v. So this is, I know why then. So now you have actually 2x, again, 2x times cosinus of x, sorry, 2x sinus of x plus, in this case, sinus of x times 2x, and then if you actually add up these two terms, are going to be 4x sinus of x, and then x squared cosinus of x. No, it's correct. This 4 is actually correct, because I'm actually adding the derivative of this one in the second term, so it's 4. So, and then we have this one is going to be minus 2, and then this is going to be minus, it's going to be 0 for the next one. So it's fine. So and then you do the same for this one. So same for this one is derivative. So this is already, this just have to be sinus because it's a constant. And then you have to do the same thing with the uv, and you have to do the same for this one, and then you're going to get this number. This is going to be equal to 0. Please verify it. Hagan esta rápidamente para ver si está bien mi ecuación. Hagan esta rápidamente, les daré 5 minutos, creo que se hacen con el lápiz, ¿no?
Perdón, hay que derivar esta, la 3.
¿Perdón? Calcule la derivada de esta.
La tercera, ¿no?
La tercera, ok, la derivada de la tercera.
Así es.
Sí, está bien, profe.
¿Sí está bien?
Sí.
Okay, that's good. So what we're gonna do to prove the multiplicity, or to find the multiplicity of these equations and its derivative, so we just have to evaluate the function in zero. So evaluate each of the functions in zero. Evalúen las 4 funciones en cero.
Profe, la hacemos en radianes, ¿no?
En radianes, sí, por supuesto. So what's the result for the first equation?
Profe, da 0 en la primera.
Yes, it's 0. So what about the second one?
Igual da
En la
0.
segunda también da
Igual a
0.
cero.
Exactly. What's about the third one?
La tercera a mí me dio -1.
You sure?
No, la
Y en
tercera.
en la
Tercera
segunda
me
me dio menos, en la segunda derivada me dio 0. No sé si estoy bien. Y en la tercera derivada es donde me da -1.
Exactly.
Sí, sí.
So if you see actually in this derivative, the evaluation of 0 in this function is equal to 0, and this one is equal to 0, and this one is equal to 0, but this one. So the last one is equal to -1, right? So in this case, so we are actually saying that we have a multiplicity equal to 3, 1, 2, and 3, because in these functions and the sets and the first, second derivative is actually 0. For the last one, it's equal to, is different than 0. So if we analyze what we said previously, so the multiplicity is n equal to 3. And then if we go back to the definition of this multiplicity, so, sorry, of the value of s, so we said that the Newton method will converge linearly with an e plus 1, I plus 1 equal to, or approximately equal to 2/3. Why? Because we have to make the operation. So you have that 3, it's -1 is equal to 2 divided by 3. So it's going to be approximately 2/3 of the error in the current step. So that's what we assume. But then,
Profe,
yes,
disculpe, ¿de dónde salió el 3?
1, 2, 3. Es el número de veces que da en este caso 0 la ecuación. Okay? Good question though. So now we actually say that we can calculate the number of steps of the Newton method required to converge. So how do? We can actually do it by just doing this in Excel. However, so one good approximation of this, so need to actually, we can use this formula. In this case, we need to satisfy this one, right? Because we need a value that is going to be equal to 6 correct places. So 2/3 is less than 0.5 times 10 to the power minus 6. This is the requirement, right? So this could be this one or smaller. So what we do here? Remember that this is actually an inequality. So if we follow the rules of inequality, we can obtain the n value. So we just have to apply log on both of the sides. So we apply both of log on this one because it's a multiplication. We can separate this one, and then log of this one here, and then the n value is going to be just the division of the applying the two logarithmic equations. And it's going to be about 35.78. This is just a rough approximation. I have to do it. But instead of that, let's actually do it using Excel. I think Excel is going to actually, show this more clearly, at least for my perspective. So let's go back to this function. So we know that this is the function. We know that this is the derivative, and we already know the Newton's formula. So let's go back to this one. So in this case, again, for the sake of my sanity, I'm gonna just paste it here. And then I'm going to delete all these ones, right? There you go. So in general, so the exercise tells me use 1 as the guess. So I'm using 1, right? And then, because I'm using 1, what I have to do is just to input the Newton's formula. So the Newton's formula says that it's going to be equal to what? ¿Cómo va la función de Newton? ¿Es igual a qué? A esta función, in this case, 1 minus what? Minus this function divided by this function, right? So it's going to be a piece of tremendous function. So sinus of this one plus this one square, right, times cosinus of this one minus this one square minus this one, parenthesis, right? So then we have to divide this one and then open another parenthesis. And then this parenthesis would be cosinus of this formula plus 2 times this value times cosinus of that value again minus this value to the power 2 times sinus of this value, right, minus 2 times this value minus 1. Is that correct? I think it's correct. So let's just see what happened. So boom. Thank God it's the same thing I got in my previous exercise. So it's easy to do it, but it requires a little bit of complexity. So what I do is just to actually just do the same thing. So be aware of this because you're going to do exercise. Fíjense bien cómo lo hago porque les va a facilitar la vida. Si no van a tener que hacer una por una, ¿eh? So just drop this down and then I'm going to make this 38. So if you remember in the exercise, with using this formula and the properties of logs, right? So we said that we need actually 36 operations. So if we go to 36 here, and we are asked to actually obtain a value of less than this, is check this out. We have to actually something to the power minus 6. So tenemos que es 1, 2, 3, 4, 5, 6. Yes. So we have actually an error less than something to the power minus 6. So it's actually 8.2 to the power minus 7. Sorry, yeah, minus 7. So we have actually met this condition after 36 operations. So if you want to compute once again the error, remember that the error is actually this one minus what we consider the true value. So this is the true value. Remember that we have to fix this up with F4 and then boom, we got this one. So I'm assuming that I got the same thing as this one. So, well, I think, well, they use as the I just change it then, just to make sure that this one. They didn't use this one. They use actually the one that I'm supposed to use in here. And then, yes, and then so didn't change a lot, so but it's pretty much the same. So here. And then what we do, hold on, B39. Well, yeah, it's the same thing, so it doesn't matter. So they're just assuming that this is the value is going to be equal to 0, because we know that the value to actually the root of this one. ¿Cuál sería la raíz para que este fuera 0? Lógicamente 0, ¿no? La raíz real. So if we actually assume that the real root is actually instead of this one is equal to 0, so what we can do is just to actually use this one, and then we use 4, and then boom. There you go. So we obtain now what we got in the last column. And then this one is exactly what I said was going to be, which is the error here divided by the previous one. So there you go. So this here. So if you think about it, so you see that the M value here, it's about 0.6 point something, right? So if we actually calculate the average, just to make something more precise, we compute the average of this one, and the average is actually about 0.67. So this is about the value of the M value, the convergence. So, and if you think about 2/3, ¿cuánto es 2 dividido entre 3? 2 entre 3. So it's actually 0.66666. So you see that actually this rule is correct. So we apply the M minus 1 divided by M. So this is about 2/3. So it's actually about that. It's not entirely correct. It's not the same, but it's pretty close. So that's this exercise gives us actually a good understanding of that. So second exercise. Well, second example actually. So we have to use this example too. Says apply Newton's method to f is equal to 4x4 minus 6x squared minus 11 divided by 4 with a starting guess of x0 equal to 1/2. This is the new, I already give you the Newton's formula. Esta es la fórmula de Newton. Por favor, háganlo ustedes para que experimenten. Yo lo tengo hecho. Ya tienen la fórmula de Newton, solamente háganlo ustedes. So you got the solution? Ya Eva se está durmiendo. O está cantando o está durmiéndose, pero no sé qué pasa.
Profe,
Yes.
¿usted sabe como cuánto tarda el correo que te manda MATLAB para la licencia?
No, no lo sé.
Mm.
So if you're actually doing this exercise, so this is what you get. Starting with 1/2. This is what you get. You get something weird. It's actually minus 0.5, 0.5, minus 0.5, 0.5. So don't think that you're actually wrong. So this is what happened sometimes. So do you remember when I told you that you have to provide a root sufficiently close to the solution? So this is actually what we call, a problem for the Newton's method. If you give us a root or initial guess that is very far away from the solution, you get into trouble. So for example, if you see the effect of changing the solution, I'm just going to show you that it's actually the same thing. So I started with 0.5 and then I used, which is this value, 0.5 minus 4 times x to the power 4 minus 6 of x to the power 2 minus 11 quarters divided by 16 to the power 3 minus 12 to the power 2 times 2x. So is this, I just, double click in the square here, and then you get this one. This is weird. So the solution isn't actually that value. So the solution, if you think about it, is actually about here. So, but what happened is just what you can see in the example. It's just, you get this tangent, and then you move to the second step, and then you get the tangent, and then you move to the second step, and it's just a cycle. It's not that good. So because we have two solutions. So for example, if I gave another point like 0.1, so instead of get 0.1, I got 0.1 is actually about here. So I got the negative root of this one, which is actually 1.36. And this 0.36 is actually the solution of the function. So I'm giving actually a 0.1. What if I get actually minus 0.1? So you see that it's actually negative, positive now. So I'm providing actually a negative root, and then I move to the next root. So this function have roots in minus 0.36 and in plus 1.36. So it had both solutions, but if I provide a number of a initial guess like 0.5, wrong, it's not good. If I give a solution of an initial guess of 1, so I get the value because I'm very close to this one. So now the root is going to be about here, and then it's going to change here. But as long as I provide something between 0.5 and, let me just see, 0.6. So 0.6 no, 0.7 no. Well, actually 0.7, yeah, now it's actually doing it. But close to 0.5, the solution is just changing to the other tangent. So be aware of, if you're using the Newton-Raphson method, then this method is very sensitive to the initial guess. Okay, so that's the Newton method problem. Well, it's not a problem, but it's just conditional, right? So there you go. It's time. We are done. We're done. So these are your exercises. So I'm gonna post these exercises not today, but on the weekend, because you already have an assignment. You have the fixed point iteration assignment. So Andrew, I don't want you to be stressed out, right? So I want you to have time and do your assignment of the fixed point iteration, because that requires a lot of work. And I'm gonna post these exercises next, I'm gonna actually do it next Tuesday, okay? So next Tuesday, I'm gonna actually give you these exercises. You already have the video because this is recorded. You can actually rewatch it if you need some help. If you have some questions, please, once again, you are actually in a very good shape for the group in the morning, because you are submitting almost all of you submitting the assignments, but many of you as well have failed on submitting the assignment. I know you have a lot of homework from other classes, but I'm going to give you this week to actually work in the fixed iteration point, so you have time to actually deliver or turn in your assignments on time. Okay, so good for you guys. So this is what I had for you today. I hope this is clear, at least for the examples we saw. The examples here are very, very simple, so you don't have to actually do a lot. This is easier than the fixed point iteration method for sure. And this is it for today. So say hello to the class in the afternoon. Hello, guys. This is the group in the morning. So I'll see you tomorrow, guys. Not tomorrow, sorry, on Tuesday. I think we have a holiday, right? On Monday. So we don't have classes on Monday, but well, you don't have classes with me though. But it's a holiday. Enjoy your long weekend and have an excellent day, guys. See you around. Bye-bye.
Yes, Profe.
Right, teacher. See you.
Bye-bye. I'm going to stop the recording now. Stop. Yes.